final presenter for our doctoral session is Ilana Szlamkowicz. She is from the Chemistry PhD program.
My research focuses on how various factors affect the spread of radioactive contaminants in the environment, as well as ways to remediate these effects. Specifically, my studies focus on a major risk-driving contaminant, iodine, whose environmental chemistry is very important to understand due to its biological affinity in humans. Our thyroids need iodine to ensure proper functionality, yet it is unable to differentiate between radioactive and stable isotopes. Additionally, our thyroids would be severely impacted if we consumed larger than normal amounts of iodine. This is especially the case with radioactive iodine. One important thing to note about radioactive iodine is that it has a half-life, or the time it takes for half of the amount to disappear, of 16 million years. That amount will pretty much never disappear over the course of many human lifetimes, and it will persist in the environment. This contaminant can already be seen in the environment at various sites belonging to the US Department of Energy, as seen by the map in Figure A. Two of these locations are the Hanford site in Washington and the Savannah River site in South Carolina. These locations were used in the past for radioactive testing as well as nuclear weapon production. On more recent years, the amount of radioactive iodine in the environment has even seen an increase due to the Fukushima Daiichi disaster in 2011, as seen by that big spike in the middle of Figure B. This disaster caused the nuclear power plant to experience a core meltdown, causing multiple explosions, releasing this radioactive iodine into the environment through both the atmosphere and into the ocean. As this contaminant has now found its way into the environment, it is important to understand the different pathways it can undergo, which would affect both the ecosphere as well as human health, with some of the pathways being seen in Figure C. My work helps to establish fundamental knowledge on the different pathways this major risk-driving contaminant can undergo in the environment, as seen in Figure D. This figure shows how this major risk-driving contaminant can interact with different mineral phases that you can find in the environment, as well as how that would cause the fate and transport and its mobility. As this contaminant is already found in the environment, it is important to understand and implement remediation strategies that will inhibit its spread into the water table. If this contaminant were to enter the water table, it would be able to spread to a much larger area, as well as have a higher likelihood of affecting human populations. Due to this, it is imperative to design remediation strategies that will inhibit its mobilization. With my work, I hope to establish fundamental knowledge as well as provide potential solutions to this topic of national importance, as established by many governmental reports, as well as provide some societal solutions to this major problem. Thank you.